Hi, everyone. My name is Yilu Fang. I'm currently a PhD student in Dr. Chenhua Wang's lab at Columbia University. And thank you so much for this great opportunity to share our recent work on knowledge-guided generative AI for automated taxonomy learning from drug labels. This work was recently published in JAMA. On the right is the QR code for our paper. So drug indications refer to the approved conditions, diseases, or states for which a drug can be safely and effectively used. Formally representing drug indication knowledge can help identify appropriate treatment and facilitate clinical knowledge management and support the secondary use of electronic health records data. A common practice to structure drug indications is to do concept mapping, where we map the indication terms to some existing ontologies like SNOMED-CT manually or automatically. However, there are two potential issues. One is mismatch granularity, and this refers to the scenario where an indication term have different granularities from concepts in the existing ontology. And here is an example. So we had these three indication terms from different drug labels: ulcerative colitis, mild to moderate ulcerative colitis, and moderately to severely active ulcerative colitis. So we can find an exactly matched concept in SNOMED for ulcerative colitis, but we cannot find semantically equivalent concepts for the other two. Another issue is the incomplete coverage, and this refers to the cases where an ontology includes a concept for the sibling term of the target indication, but does not have a semantically equivalent term to the target indications. And here is an example. We can find an semantically equivalent concept for metastatic castration-resistant prostate cancer, but we failed to do so for metastatic castration-sensitive prostate cancer. So although the existing ontologies facilitating various concept mapping applications, they still have limitations in accurately and comprehensively normalizing indication concepts. And these lead us to think, why not establish a taxonomy for drug indications directly? So in this study, we aimed to integrate large language models and real-world evidence to develop an automated pipeline to first extract indication terms from free text drug labels, and then derive their subsumption relations and further create a drug indication taxonomy to organize drugs. Before I introduce our methodology, here are the few things that I wanted to specify. First, indication concepts are nodes in the taxonomy, and indication terms are mentions extracted from free text drug labels, and they will be linked to concepts that represent their closest ancestors within the taxonomy. And based on our understanding, an ideal drug indication taxonomy should be able to differentiate distinct indication terms, and those semantically equivalent terms should be linked to the same concept, and there should be no further child nodes that distinguish these terms. So we may need to examine the concept to concept and concept to term subsumption relations. This means that we are trying to answering questions like, does concept A subsume concept B, and does concept A subsume term C? Now let's walk through the general workflow of drug indication taxonomy development. So we retrieve free text drug labels from DailyMed, from which we extracted indication terms using GPT-4. We then post-process the indication terms using both GPT-4 and regular expression to eliminate terms with the same meanings. At the same time, we created multiple versions of high-level indication categories using GPT-4. And then the domain experts help select the best version for the following steps. Here, an indication category is a concept or a node in the taxonomy. We then classified terms into these categories by checking the subsumption relations between a concept and a term using GPT-4. Okay, so then an iterative crawling procedure will be applied to create a subtaxonomy for each indication category, and eventually we created our drug indication taxonomy. And now let's delve into the iterative crawling procedure to create the subtaxonomy for each indication category, or like the concept. So first we computed the information of a concept using real-world evidence. So here it characterized the similarities among indications subsumed by the concepts. And here the indications were represented by their related drugs, and drugs representations were derived from real-world patient data. Then we created subcategories of the concept and classified terms into these subcategories using GPT-4. And then we computed the information of the subcategorization. It characterized the similarities of indications for any node in the subtaxonomy. We then calculated the information gain by subtracting the information of a concept from the information of the subcategorization. And this indicates how well the subcategorization increases the similarity among indication terms falling under the same concepts. And if the gain is large enough, we added these subcategories to the main taxonomy. We iterate this procedure on each leaf node in the updated taxonomy. And here is a demonstration example. From these drug labels, we extracted the following 3 indication terms, which were peripheral vascular disease of arteriosclerosis obliterans, thromboangiitis obliterans, Buerger's disease, and Raynaud's disease. On the right is the taxonomy we created eventually, and the indication term Raynaud's disease was linked to the concept Raynaud's disease, which is a child concept of vascular diseases. And vascular diseases is a child concept of cardiovascular diseases. So eventually, we extracted 4,100 indication terms from 46,000 human prescription drug labels from DailyMed as of February 2023. And after post-processing, we had 2,900 terms left. And these terms were linked to 1,100 RX norm drugs. Here are the high-level categories of the taxonomy. So we had categories like cardiovascular diseases, respiratory diseases, digestive system diseases. And just to make an example, there were 234 indication terms falling under the cardiovascular disease category, and there were 189 drugs linked to any of these indication terms. So we picked 3 high-level categories and created their subtaxonomy. We investigated the depth of the subtaxonomy, which is the number of levels from the root node to the deepest node. And for all the 3 categories, they all had a depth of more than or equal to 10. We also investigated the width, which is the number of child nodes of a node in the structure, and the median width was all 3. We also counted the unique nodes and unique leaf nodes in each subtaxonomy. And genitourinary system diseases had the most complex hierarchical structure. It had 516 unique nodes and 349 unique leaf nodes. So here is the subtaxonomy for high-level category of cardiovascular diseases. So all the subtaxonomy we created meet the desiderata for controlled medical vocabulary. For example, it has various levels of code granularity, and the depth is comparable to its counterpart in SNOMED-CD. It also has a polyhierarchical structure where a concept can have multiple parent concepts. I would also avoid the use of not elsewhere classified and maintain the taxonomy consistency with no acyclicity through some rules we defined. We'd also assess the accuracy of concept-to-concept and concept-to-term subsumption relations. We invited 3 domain experts for this evaluation, and we calculated their inter-rater reliability. So for concept-to-concept subsumption relations, we'd achieved a high accuracy across different raters and different categories, and we achieved a good to very good inter-rater reliability. So this indicates that large language models are good at constructing their own hierarchy for drug indication. As for concept-to-term subsumption relations, the accuracy varied, and we can only achieve fair to moderate reliability. So this indicates that determining concept-to-term subsumption relations is a complex task, even for humans. So in summary, we proposed an automated pipeline that integrates large language models and real-world evidence to generate an effective taxonomy, which is optimized to distinguish between drugs indications and organized drugs. And based on our experiments, large language models works well in deriving their own concept hierarchies, but they fall short in determining the subsumption relations between LM-generated concepts and terms in unregulated language from free text labels. And this is also the hard task for humans. And we provide a framework for taxonomy learning that can be applied beyond the context of drug indications. Okay, thank you so much. And if you're interested in our work, please scan the QR code below. And if you have any questions, feel free to send me an email. Thank you.